Thank you very much. So thank you, Bob, and the rest of the organizing committee. I was delighted to be asked to do a presentation like this to the community, especially geared towards younger folks. As Bob alluded to, I work up at Los Alamos in what's called the Lujan Neutron Scattering Center. I'm going to tell you quite a bit more about that today as the talk goes on. And he stole all my thunder. I was going to tell you all this about myself. I was actually trained in material science at UC Santa Barbara. And before that, I actually had a bachelor's in chemical engineering at the University of Maine. And so often as we go through our careers, we change direction, and the direction I took I'm really excited about. Other than atomic structures and diffraction and all the things I'm going to talk to you about today, things that I enjoy, weightlifting. This was me lifting at the Olympic trials in 2008. And I have a 2-year-old son. He's not old enough quite yet to enjoy talking about this type of science with me, but I hope someday soon he will be. And my husband and I, of course, really love the Southwest. We lived here for the last 5 years, actually. We were postdocs at the laboratory first, and then we became staff members in 2010. Okay, so today I'm going to tell you a little bit about crystallography, what that is, and material structure and why you should care about it. Then I'll tell you a little bit about neutron scattering at a facility right in your backyard up at Los Alamos, the Los Alamos Neutron Science Center, or LANCE, and the Lujan Center where I work. And then, if we have enough time, I'll tell you about some applications of this type of science, materials studies with neutron diffraction, and show you the great diversity of things that we study at this center. I hope you ask me questions as I go along. I'll probably ask you a few questions to try to get you engaged, so please entertain me and we can have a nice back and forth. This stopped advance. There we go. Okay, so molecules and crystals. Depending on what grade you're in, you may not have heard of these things. I noticed there's quite a few really young people in the crowd. So a molecule is a well-defined unit that has a fixed number of atoms. Can anyone think of a molecule that they've heard of? What is H2O? Water. Very good, water. How about CO2? Has everyone heard of that one?
Carbon dioxide.
Very good. So you have heard of quite a few molecules. This is the CH4 or methane molecule. That's a fuel. Crystals, on the other hand, are made by repeating a certain unit of atoms in all directions. So like this little scientist here who's building a wall, each brick is identical, and if you stack them in 3 dimensions, you build up a 3-dimensional object that you can hold in your hand, for instance. And so these types of crystals have what we call a unit cell, and again, you can think of that like a brick that makes up matter you hold in your hand. Okay. Crystallography is the science that examines the arrangements of atoms in those types of solids. And actually, 2014 has been named the International Year of Crystallography by the United Nations. So particularly, the Education, Scientific and Culture, or UNESCO organization of the UN, has done this. You can find out all about this on their website, iycr2014.org. And this year was specifically chosen because it's the centennial of X-ray diffraction, which was discovered around 1912, and we'll talk a little bit more about that later. And it's also the 400th anniversary of when Johannes Kepler observed in 1611 the symmetry of ice crystals. So we do get snow here. Have you noticed something about the structure of a snowflake? How many sides does it usually have?
6.
That's right. So why does it often have 6 sides? It doesn't always have 6 sides. Sometimes it has 3 or 4, but they often have 6 arms. Anyway, he discovered at that time that you can tell something about the symmetry at the atomic level in matter by its external shape. So that's what I'm going to talk about here. So this is H2O, which our friend here already told us was water. This is one molecule of water. Now, when water is in a liquid, these molecules are moving around quite fast. Not as fast as if they're in the gas, so in the air, water vapor. But they're moving around, and they're loosely correlated or organized one to the other. But as these start to freeze, if we cool down water, they start arranging in this way. So here's the 2 hydrogen and the oxygen atom there in that molecule. And what happens is you get hydrogen bonding between the molecules, and so they start arranging like this. And then, depending on the exact nature of the crystallization, so exactly what pathway the cooling down happens as a snowflake falls from the sky, right? It's going through many different temperatures, meeting many different types of molecules, and so it directs different shapes, but it often keeps this overall hexagonal symmetry. Okay, and so I'm going to actually pass a few examples around. I have these 2 examples with me today. So this is a fluoroapatite crystal that I have in my hand. It's not a perfect crystal, but if you look at it, you'll see it has this hexagonal external symmetry. And that is a reflection in this case of its internal hexagonal symmetry. Okay, apatite, interestingly, is the type of structure that your teeth are made of. And there's fluoride in your toothpaste, right? Any idea why? Well, this is a fluoroapatite crystal. Fluoride makes the apatite structure much stronger. And so there's something like this structure in your teeth enamel. And brushing with fluoride toothpaste makes that stronger. Okay, I'm going to pass this around. So again, this is fluoroapatite. And you can see its external shape, which in this case is related to its internal shape. And this comes from the Yates Mine, Otter Lake, Quebec, Canada. All right, the next example I have is actually fool's gold. Does anybody know what the mineral for fool's gold is? You heard of that?
Iron pyrite.
Very good. It is a pyrite. So this crystal structure, pyrite, is actually a primitive cubic. So its bricks are cubic in structure, which means 3 equal sides. I should have probably told you what hexagonal meant too, but you can see it as it's being passed around. Okay, so the internal symmetry is again reflected by its external shape. Now, if you have very nice growth conditions for these minerals, sometimes you can infer the crystal structure from the outside shape like this. But that's actually quite unusual. Most materials that you come in contact in the world don't look like their local atomic structure at the very smallest level. And for those materials, most materials and a lot of functional materials in the world, we actually have to use sophisticated structure analysis methods to determine those structures. And that's what I'm going to be talking to you about the rest of this time. And shape and external shape is one property of a material. Can you name some other properties of materials? How about color? It's a property, right? What about more?
Like weight?
This is density and weight can be a property of a material. More exotic properties, such as magnetism or electric polarization. So if you apply a magnetic field, the atoms move. All of these types of properties, it's very important to know what the underlying patterns in these materials are to understand and utilize those properties. Okay, so I'm going to give you somewhat of a familiar example. That's what we're going to jump off with before we dive into advanced functional materials. So does anybody know what the chemistry of diamond is? What is diamond made of? What's the atom in diamond? Carbon, right. How about graphite? So what the end of your pencil is? Carbon, right. So the formula for graphite and diamond, the atomic formula, is the same. It's just C. So why do they have such different properties? We're going to talk about that. And then we're going to talk about a third form of carbon here. Okay, so the first crystalline form of carbon I'm going to talk about is diamond. This is actually a model of the structure of diamond. Each of the black things here represents a carbon atom, and then each of these red pieces represents a bond between the carbon atom. And so if you look at any one of these atoms in the center, because this is just a piece, you imagine it goes on in all dimensions forever and ever and ever. Can you see how many bonds there are to an atom in the center?
3.
There's actually 4. So there's 3 kind of in one plane and then one below. So it's a 4-dimensional bonding network. And that makes diamond really hard. Okay, so what are the types of things diamond is used for? Yeah?
Rings.
Right, jewelry.
Cutting stuff.
That's right, cutting, because it's very hard. Yeah?
Record players.
Oh, the needle. Okay, very good. I've never heard that one before. All right. Yeah, so things where you want a very brilliant or very hard material. Now, this diamond is not as pure as this one. Some impurities can change the color of the material. It still is very hard. So industrial diamonds, the ones, I guess, at the end of a record needle, and the ones you use for cutting are more generally like this form. And then the very brilliant ones are used in jewelry. It takes lots and lots of pressure in the earth to make a diamond. It's a precious mineral. And we do have some routes to make synthetic diamonds, but they're very small, and they're not as beautiful and brilliant as this is. Okay, so again, because each carbon atom is bonded to 4 others in a 3-dimensional way, this material is very hard. It can scratch glass or other very tough things, cutting and grinding, jewelry, etc. So we can pass this around. You can take a look at it. All right, our second example is the graphite. This is a model of the structure of graphite. Again, the same chemical formula. It's the structure of these materials that make them so different. Chemistry also makes materials different. Today we're accentuating structure. Okay, so what you'll notice about this material is it has several types of bonds. It has these stronger red bonds that go between carbon atoms that are in one plane. Then it has these weaker, call them van der Waals type bonding, between layers of graphite. So anybody know what some of the uses of graphite are? Yeah?
Pencils.
Right. Lubricant, that's right. Yep.
More contemporarily, graphene is made from it.
That's right. Graphene is actually like single sheets of graphite. So it's a more disordered form of graphite. You can often make graphene by pyrolyzing or heating these types of graphite structures.
A question about these models.
Yep.
We've got the carbon in the center and
Yep.
then the bonds between them. How accurate size-wise is that relationship for, like, I guess, the outer valence of one to another and that size relationship of connecting?
So not very, well, it depends. So if you were thinking of this little black piece as the nucleus, it's way off.
Right.
Because the nucleus is so small.
But if it's the outer valence.
Yeah, I think it's still off, but it's a lot closer. So in these distances in graphite, it's about 3.3 angstroms between the atoms, and I would say, yeah, it's still quite off. Like these are too long compared to these are too short compared to the size of this. Right, it would be more spread out if it was to scale of like the outer electrons in the material. Yeah. But I think to make a model you can hold in your hand, like this is a good way to go.
Because isn't that important when atoms are in a molecular relationship, they're sharing electrons because of so they can still be far apart and yet still be communicating by the...
Absolutely. These stay together because there's real chemical bonds. So there's different types of bondings in solids. You may have heard of words like ionic and covalent and van der Waals, which I just told you. The bonds in diamond are those strong covalent bonds. And so those are much stronger, more tightly bound one to the other. This is a much weaker bond here. This is actually pi-pi bonding, which I won't get into. It's a little technical to talk about orbitals. But it's, again, a little bit weaker. But still, the bonding in plane is very strong. So the way your pencil graphite actually works, it's not lead, remember. It used to be lead. We don't have lead in pencils anymore. Is when you press your pencil on the paper, you actually leave these sheets behind. So they slough off, and so you're leaving these nice sheets on your paper. That's how it works. And so if you can imagine, you put some shear on your pencil as you write, and these come off. And then
the red bonds are way stronger than the yellow.
That's right, absolutely. And that's how the lubricant works as well. So same idea.
How
I
much
pass this around.
stronger are the red bonds than the yellow bonds?
Oh boy.
Like this strong or like...
Yeah, they're a lot stronger, but I can't actually tell you. I'll have to look that up. Good question. Okay, so as you all know, because you told me, each carbon atom is bonded to only 3 other in the layers. This results in a soft material, and it will leave a mark on the paper as you move it along. It's also used for lubricants. Great. Okay, has anybody ever heard of a buckyball?
Yeah.
Yeah, you have?
Yes.
Okay, this is another newer type of carbon that was discovered in the mid-1990s. So C60, it's a little bit different than the ones we just passed around. This is actually a molecule, okay? So you notice no dangling bonds here. Because it's a molecule, so you can isolate a powder of this material if you make enough of it. But if you put it in a solution, it actually dissolves in solution. So this molecule stays the way it is, but they separate from each other. So it's dissolving in the solution, and it changes the color. Do you have any idea why it might do that? Well, it's actually because this structure is around a nanometer across, which is around the wavelength of light. And so it does some interesting things interacting with light because of the size of this molecule. This C60 molecule was discovered, in 1986 by these 3 guys, Robert Curl, Harry Kroto, and Richard Smalley. And they earned the Nobel Prize in the 90s for it, I think 1996. You may have noticed, I should have asked you this on the slide before, it looks like a shape you're probably very familiar with. This is exactly the type of hexagonal and pentagonal tiling that you find on a soccer ball. And so that's really neat that we found this in nature. So if you... It can be created synthetically, but after it was discovered synthetically, they went back carefully and looked at, for instance, carbon black in tires, and it's there. Wow. At a low concentration, but you can find, accidentally made, maybe is a better term. I don't know about naturally. Probably, though, volcanoes and such. Yeah.
Did they design the soccer ball after this atom or like before? Or it just happened to be the same or what?
It just happened to be the same, but you know why? If you want to make a sphere with flat shapes, you can only approximate it. You can never really make a complete perfect sphere with flat shapes. So there's only a certain number of ways you can tile a sphere, right, and make it close to the shape. And this way, this is the least number of pentagons and hexagons you can tile something close to the sphere with. You can make bigger ones with the same shapes, and you can make, I used to have a really nice long nanotube. So if you imagine splitting this in half, you can take a graphene sheet between it and you can make a nice long tube. Those are called Bucky tubes, which were discovered quickly after these were. So if you can imagine this being the caps of a tube, you can take a flat sheet of graphene, so very much like the sheets you just saw, and make a cylinder, and then you cap it with these things on the end. And so that's a Bucky tube. And yeah, so I forgot my train of thought a little bit here, but you can make a lot of cylindrical, different size cylindrical shapes and different sizes of cubes with these tilings. But again, you can never make it perfectly spherical.
Okay, so what is like the difference between the red and the white ones?
That actually is just a guide to the eye for modeling. There really isn't. So you'll look at this and you'll see the pentagons are all red, and then they're attached with white. And that's just a guide to the eye when you're building the model.
Actually, I have these like toy things. They're really cool. They have magnets. And
Yeah.
they have different shapes like triangles and squares and
Right.
pentagons and stuff. And I can actually make that shape with them.
You absolutely could. And I used to have a picture of that, but I didn't put it in this talk. Good idea. So I also can pass this around, and if you want to play around with connecting these and trying to make different shapes, you can. So feel free, if you're a young person, to take some of those out and play around with them. Okay, so again, these carbon atoms are bonded to 3 others within this 60-atom molecule. It can dissolve and form a solution because of that. And the solution, again, contains individual molecules. You can also crystallize this into a larger crystal where this is the repeat unit of a lattice. And that's how the detailed analysis of this material is completed. Okay, so now we're going to switch gears a little bit, because I want to get to the part of the talk of what we actually do to solve these structures, okay? Are we done with the diamond structure yet? Because I'd like to have it back to show you something. The first one I passed around. So the way we actually study materials with diffraction is we look for things called d-spacings. Okay, here we go. So you might notice, if you look at this structure in different ways, you can see, you can line it up so that you see planes of atoms at different angles. Okay, that's important. And the distance between those different planes, I gave 2 examples here. So this is the equivalent atom here in this repeat structure. If I draw a line through it and then through here, there's this distance between these planes of equivalent atoms. I can draw a different d-spacing between these planes of atoms. And so this distance between those planes is different. So we don't have a lot of corn around here, right? But how many of you have driven by a cornfield and looked at it? Yeah? Have you ever noticed that you'll see a wall of green and then all of a sudden you'll see a space as you're driving by? That's exactly what we're doing when we send X-rays and neutrons through a crystal. At certain angles, you can see those spaces between the order, okay? We'll talk a little bit more about that later. And I don't want to get into lots of details, and this is the only equation I think I put in my talk, so. But there's something called Bragg's law, which tells us how a diffraction angle depends on a wavelength of radiation. So light has a wavelength. Different types of light have different wavelengths. Neutrons and X-rays and electrons all have an energy and a wavelength, okay? You may, depending on where you are in school, you may have heard of this particle form of matter and wave form of matter. Here we're talking about the waves. But anyway, this is the relationship that includes these d-spacings and an angle of my measurement in this case with a number of wavelengths of the radiation. All right, and so there's lots of things in life where you can observe diffraction happening. So one is, have you ever noticed this on a CD before? Yes. Shiny kind of stuff? Well, that's actually because there's little grooves all the way around that. And those grooves happen to be on a length scale that interacts with the wavelengths of visible light. And so you get these patterns. Same thing in butterfly wings and some beetles. Same type of thing is happening. But that's a much higher length scale than what we use when we're using neutrons or X-rays to look at atomic positions in materials. Impressively, William Lawrence Bragg and his father, Sir William Henry Bragg, discovered this 1913-14, and then they won the Nobel Prize in Physics in 1915 because they used it to determine crystal structures with X-ray diffraction, and they started with, who knows what sodium chloride is? Any idea? Salt, right. Salt, diamond, which we talked about, zinc selenide, another one, sulfide, sorry. They did zinc selenide later. So William Lawrence Bragg was actually only 25 when he did this. I find that incredibly impressive. I'm 32, so. Anyway, really neat. So again, here's the structure of diamond, and depending, just like the cornfield, which way I look at it, I see different interplanar spacings in the material. And here are 4 of those shown here. So A, B, C, D, just looking at different interplanar spacings. That will be particular for every structure, okay? So remember the graphite we passed along? That has interspacings between those planes. But then also, if you turn it on its side, there'll be ones that are in those planes. So a diffraction pattern, and here's the theta we talked about. So this is the angle. You get intensities, so you get light, you get your radiation, whether it's X-rays or neutrons, passing through at these planes. You have collective interference is one way to call it. And this is the signal of the pattern corresponds, again, to different planes of atoms in the structure. So this is what we call a diffraction pattern. Okay. And so here I have some simulated diffraction patterns for the 3 structures we just talked about. Again, they're all carbon, right? It's the only thing in the formula. They all have very different properties. That's all related to the structure. And we get these different d-spacings, interplanar spacings, depending on the structure. So it is exactly like a fingerprint for a structure. This is how we begin to do structure determination. And what's really cool is for simple structures, you can often just figure these out. For complicated structures, you definitely need to do modeling. So we spend a lot of our time collecting these diffraction patterns with sophisticated instruments and then modeling those patterns with sophisticated software. But the basic idea is very simple. Now I'm going to make things a little more complicated before we get into some real examples. So here was our very well-ordered cornfield. What do you think happens when you have vacancies or dopants, so something in the cornfield that isn't corn, or you have a grain boundary, or a boundary between 2 different structures, or a bend, this kind of modulation? What do you think happens to those Bragg peaks? Any ideas?
More complex.
They would be much more complex. Do you think they would change shape? That's exactly what they do. So sometimes they can completely go away. If we disorder the structure enough, right, there's no constructive interference anymore, or there's less constructive interference. It affects the height and the width and many characteristics of those Bragg peaks. And so in many functional materials that we study at Los Alamos, the structures are more like this and less like this. The very first examples in the crystals I passed around today, they're much more like this, okay? So now, that was my introductory part of, yep.
For the box of things that need to come back around all the way.
Oh, sure, I don't know where the, does it still have pieces in it? Yeah, I think it maybe did this side of the room and not that side, so. Okay, great.
Could you repeat the questions when someone asks a question, because sometimes we can't hear, so we don't know.
Yeah, absolutely, thanks. They just asked for the box again to be passed around. Okay. So, like I said, actually in our backyard we have this wonderful world-class facility to do these type of measurements. And it's a neutron scattering facility. All right, so up in Los Alamos, have you all been up there? You probably haven't visited the Los Alamos Neutron Science Center. You have to have a special pass to get out there. So, but it's a user facility, which means we actually work with scientists from all over the world on whatever exciting problems an external scientific review committee decides are most exciting. So scientists go there to study the relationships between material structure and their properties, things we've just talked about. The Lujan Center is actually at the end of the Los Alamos Neutron Science Center. This is the LINAC, the 3/4 of a mile long proton accelerator that we use to make neutrons, or release neutrons is probably more accurate. So you can actually make neutrons in a nuclear reactor, like a power plant type reactor, or you can do them with an accelerator like we do in this state. So this accelerates protons to 85% of the speed of light. That's 158,000 miles per hour. And then we smash those protons into a tungsten target. Do you have any idea why we use tungsten? Do you know anything about tungsten? It's heavy, right? It has lots of neutrons and protons and electrons in it. So when you smash into tungsten, it releases a lot of neutrons. That's why it's used. One of the reasons why it's used. And so these neutrons are emitted from the target, and then they go to different end stations to be interacted with matter, and then we study that interaction. There's many different types of experiments there. Why neutrons? I also said you could do this with X-rays. Neutrons are actually a lot more expensive to produce, so why would we use both? Well, I really like to show this, although it's not diffraction, it is showing you how X-rays versus neutrons are attenuated by different materials, how they're stopped by different materials. So when you go to the hospital and get an X-ray, they're using X-ray radiation, right? Well, X-rays interact with the electron clouds and materials. And so the heavier elements show up more readily than light elements. And so in your body, because your bones have calcium and other heavier minerals in them, you see the bones much more readily than you see tissue. It's actually just the opposite in neutrons, happens to be. So neutron interactions with matter aren't so straightforward. They don't go cleanly with, say, increasing atomic number or heaviness of the material. Instead, they're a little bit random, but thankfully, there's things like hydrogen and lithium and light elements that are very difficult to see by X-rays that you can see readily by neutrons. So here is an image made with neutron scattering, and this is a very heavy steel or lead, I'm not sure, container, and you see right through that heavy material, and what you actually see is the rows inside with neutrons. So you have this really different sensitivity to different types of atoms, neutrons and X-rays. In addition, neutrons deeply penetrate material because the nucleus that the neutrons interact with is so much smaller compared to the electron cloud, which the X-rays interact with. So where you can only sometimes go through very, very thin layers with X-rays, you can go through something very thick like this with neutrons. Okay, so at the Lujan Center, there's a number of diffraction beam lines that we use. I'm actually the instrument scientist for this one. There's a picture of it here. It's called the Neutron Powder Diffractometer, NPDF. It sits right here in our large experiment hall. We also have the spectrometer for materials research and temperature at stress, which I'll show you an example for in a few minutes. High intensity powder diffractometer, HIPD, here. High pressure preferred orientation neutron diffractometer, or HIPPO, is there. I'll show you an example from HIPPO as well. So depending on the particular science question we're asking, we'll use a different instrument. And there's other neutron techniques, which I'm not going to talk to you about today, that round out the rest of the facility. I could give an entire talk, and one of my colleagues could give an entire talk in any one of those techniques. So. Okay, so the last few minutes I want to spend actually showing you some of the more current real-world applications of this type of study. The first example, sorry, this is not advancing so well, is actually an example of improving the efficiency of solid-state lighting. Have you guys ever heard of that term? You heard of LED lighting, maybe? Yeah, you've heard of that? Okay. So I'll tell you a little bit about how that works and how we've been involved at Los Alamos, working with Professor Ram Sheshadri at UC Santa Barbara and his graduate students, at figuring out why this phosphor material, I'll tell you what a phosphor is, kind of tell you what a phosphor is in a minute too, is used in LEDs. If we can understand why this one works so well, we could use it as a guide to search for new ones. So here over here is a plot of different lighting technologies over the last 150 years or so, and their luminescence efficiency, so that's luminescence over power figure. And you can see incandescent lighting, and halogen, fluorescent, sodium vapor. Don't worry about what all those are. White LED lighting, which you're now starting to see in especially businesses, but people are starting to put them in their homes too, started out way worse than, 150-year-old technology, and then very rapidly has increased to being the most efficient lighting we have in the world. I'll skip through this part. These are both professors at Santa Barbara who kind of paved the way for this blue LED-based white lighting. So the way this works is you have this blue LED, so you have an LED, so a lot like this laser that I have, but blue, okay? And then you take a phosphor material that, when excited, emits orange-yellow light, and when you mix those two, you end up in the center of this color chart and you get white. So that's the idea behind the technology. The material that was first used is the one actually that we're mostly still using, just extremely lucky to start out just about on the best one. It has very high quantum efficiency and a high resistance to thermal quenching, which are two metrics we have to pay attention to in lighting efficiency.
Can you stop just a second?
Yep. Color quality is still not quite great. You know that if you're in this solid state lighting, it's not as good as the sodium type lighting. It seems weird to people. It's cold. So it doesn't have enough of the yellow orange. And so we're looking for better color combinations. And this is a very detailed study on the best material we know so far to see if we can infer the type of structural features that would lead us to better phosphor materials.
So
Are we good again, or?
Yes.
Okay.
on a spectrograph, this would show like a big spike at blue and at orange.
That's right.
So they add up to white, but they're not a full spectrum.
That's exactly right. And so the color still, your eye can tell. Your eye is very sophisticated. Yeah. Okay, so this is something called the garnet structure. It's a cubic structure. So again, the three sides of this unit cell are the same. You can see this is a lot more complicated, right, than the examples we started with. And what we really want to know is when you put cerium on this site here, so there's one cerium in place of one of these guys, what is the environment of the cerium? That's the active phosphor element. And so we do this type of experiments to relate to the optical properties, and then we create design rules for new phosphors. So this is the type of question and answer inquiry we're doing on many different materials types at this neutron scattering center. So here is, again, much more complicated diffraction patterns. And now we have them fit with these red lines, and there's a difference curve here. So very nice fits to both synchrotron, which is a type of X-ray, high-energy X-ray, and then neutrons from our facility. And we get a very nice depiction of that structure. So this is not just a cartoon. This is actually created, this picture is actually created from the analysis that we've done over here. Okay, so again, and what we find is that it has an extremely rigid lattice compared to other materials, meaning that the atoms don't move much from their ideal locations. So all materials, unless at any finite temperature, the atoms are vibrating. And if there's disorder in that structure, or there's some type of dynamic ordering that structure, they can move a lot, actually, and they move in different directions. This one has very small ellipsoids, we call them, where you will almost always find the atoms. So we call that a very rigid lattice. And so this is probably a little bit too much detail, but the cerium, when it goes in to YAG, doesn't distort the lattice like you would expect. So if you all of a sudden replace one atom in a repeating structure with a totally different atom, you expect things rearranged somewhat, and they really don't very much in this. So it leads to this very large, what we call crystal field splitting, which gives you this great efficiency that we've been talking about. So anyway, you can actually combine neutrons. You can use neutrons to study, in a similar manner, all types of technology: batteries, fuel storage, better catalysts, so to make chemical reactions go better, stronger magnets, anything you can think of, even concretes. So this is a work of my former postdoc, Claire White, who's now a professor at Princeton University, and she was studying the atomic structure of alternative cements. There's actually a company in Santa Fe that makes these. I forget what the name of them is, but these cements use a different chemical process, and they emit far less CO2 into the atmosphere. And it's one of the leading causes of CO2 emission, actually, is concrete curing. Over 40 years, it's still sending CO2 out into the atmosphere. Another thing we're doing in my group is scientists have this crazy idea that from a coal power plant, you might be able to pump CO2 back down in the ground and store it. This is called carbon sequestration. You may have heard of that. But the problem is we don't know a whole lot about the stable forms of carbonates at temperatures and pressures in the Earth. And so we're doing this study. Don't really have any great results to show you yet, but we're building a sample environment, again, because neutrons can penetrate things. You can build a sample environment to do things under temperature and pressure. We're going to look at the mineral growth of calcium carbonates with CO2 at crustal, like the Earth's crust temperatures. And what I have here is actually 4 different versions of carbonate minerals. The first 2 are actually both calcite. That's the most stable form of carbonate mineral. You'll notice how different they are. Again, they're the same formula, and in that case, They're even the same basic structure, but just like a snowflake can look different one to the other, those two materials look different. This is a less stable form of calcium carbonate, and these are actually all from different places in New Mexico. This one's called aragonite, and it has quite a different crystal structure, but again, the same atomic formula, CaCO3. So we're starting that study. And then I'm just about out of time. I want to leave some time for questions. So I'll go really quickly through these next two examples. I told you I'd tell you a little bit about what SMARTS and HIPPO do, our two other main user program diffractometers. And so Professor Chev Nguyen at Columbia University, along with our scientists at the SMARTS instrument, have been looking at the load carrying capabilities of suspension cables on suspension bridges. So you may be aware, you may not be, that our bridge infrastructure is severely out of date in this country. And bridges that were designed for 40 years of service are often in 60 or 70 years of service. And so figuring out how healthy these cables are, or how we can fix them if they're not, is of great societal importance. And so they've done a really nice, very basic study of these bridge cables are packed in bundles, actually quite big bundles. They approximated the big bundle by 7 in this experiment. They have this nice stress strain rig they put in the neutron beam, and they can pull on these and see how they act when they put a defect in one of the cables. So for instance, we cut a little defect or slice in the middle cable, and then we pull on it and see what happens. And remember the disordered cornfields I showed you? Well, what happens when you start straining the material is you start getting different atom-atom planes in your material, right? And it can correlate with the direction of the strain or stress. And so you can do this analysis for different locations and decide how each of those different locations are stretched. And so they've done some really nice work here that's been published that is going to help determine the load carrying capabilities of our existing suspension bridges and also better design new cables for the future. One of the cool things they found is that clamping the strands at certain locations really help in the stability of these things. So it may not be that we have to go and fix all of the defects that have shown up. We might just be able to go clamp around them. So that was really cool societal. And this one is kind of surprising to people to find out that you can learn something about meteors from neutrons. Okay, so Rudy Wank's group, Professor Rudy Wank at UC Berkeley, he's a very well-known geologist. And you may have seen this meteor crater in Arizona, which I think is only maybe 150 meters across, 200 meters across, okay? This is like several kilometers across. So this guy, the Vredefort Dome area in South Africa, they think impacted the Earth when really there was just algae here. So no bigger forms of life. And it was quite a few times smaller than the one they discuss as wiping out 75% of the Earth's life quite a few eons later. I'm not a geologist, so I don't know the history so well. But where do neutrons fit in here? Well, Rudy and our team at HIPPO, particularly Sven Vogel, who's my colleague and the instrument scientist there, they took a specimen 30 kilometers away from the impact site of this Vredefort formation, and they put it in the HIPPO diffractometer and looked at it. And what's really special about HIPPO is it has all these detectors at different angles. It's quite a different setup than most of our other diffractometers. And what they're able to do is correlate the diffraction patterns, they're very different in these different banks, with what we call a texture analysis. This reveals, for instance, in this case, the direction of the compressive shock wave. So they call it a piezometer, so that's a measurement for stress, that can help geologists uncover prehistoric clues to the Earth's past. So you can imagine collecting different samples from different places. When an impact site is that old, it can often be hard to tell how it hit the Earth and exactly how that propagated through the crust. And this is kind of a very far, well, it shows you the breadth of the research that can be done with neutron scattering. Very diverse. Okay, so I'm done here. As a summary, 2014 is the International Year of Crystallography. I think it'd be great if you guys remembered that. Most countries are putting out postage stamps with cool crystal structures on them. I don't know if the US has theirs out yet, but you might see that. And remember that material structure, not just the chemistry, is very important to understanding and improving their functionality. Neutron scattering is very helpful and sometimes critical for studying types of matter. And in your backyard, you have this world-class characterization facility that people come from all over the world, many different universities in the US and elsewhere and other government facilities to use it. There's really only a handful of facilities like it throughout the world. And many types of scientists, engineers, geologists, chemists, physicists, biologists use it. And in terms of acknowledgements, some of the introductory material actually I did with my advisor at the Materials Research Laboratory in Santa Barbara. I've enjoyed doing outreach for many years, and that started with him. And then here were the research groups of the examples that I showed you. And for all of these academic researchers, there was a counterpart like myself at the Lujan Center who enabled that science at that facility. So I'd be happy to stick around and discuss with you guys and hopefully get all my stuff back eventually. Thank you.